Hello, we are team number 1. My partner Sofia and I, Chris, we are going to present our statistical project about the water quality in Mexico. The content that we're going to be talking about during this presentation is the following. First, we're going to present what CONAGUA is, then the contribution of the dataset, the description of the data and the variables, the type of variables, and the relationship among variables. After that, we're going to see the problem definition related to the status of water quality and then the objective of this project. After, we'll see the main decision for this data, meaning the scientific hypothesis and their statistical hypothesis. We build 3 scientific and 5 statistical hypotheses. Then we will present the descriptive statistic for the 5 variables we are focusing on. Then we're going to talk about the outliers, the decision we made regarding them, if we transform or not the data, and the distribution we chose with the goodness of it. In order to make the best decision, we are going to present a simulation of the distribution for each variable that we made, and after we chose the distribution, we will give a clear explanation and identification of the parameters of the specific distribution. And finally, some conclusions. CONAGUA is the National Water Commission, and it is an administered body in charge of managing, regulating, controlling, and protecting national waters in Mexico. In 2019, CONAGUA established 2,764 water quality monitoring sites throughout the country. The main purpose of this study was to make a proper analysis of the status of the water quality in each state of Mexico. The contribution of the study will allow to demonstrate the status of the worst water quality state in Mexico, which is Tabasco, in order to take action to provide and improve the quality according to the previously parameters established and following standard water quality guidelines in order to provide an equal quality of life for all their citizens and living beings.
Okay, now we're gonna talk a little bit about the variables. This analysis is focused on the surface water quality, and we are considering 6 variables which are used to measure the degree of contamination of the water monitored in the majority of the sites. First, we have biochemical oxygen demand at 5 days. This is measured in milligrams per liter, and it indicates the overall concentration of organic substances by their effect on the respiration of a microbial biomass. Since 1908, this analysis is measured at 20 degrees Celsius over 5 days in the dark. Then we have chemical oxygen demand, which is also measured in milligrams per liter. It indicates the amount of substances that are dissolved or in a suspension in a liquid sample that can be oxidized by a chemical medium. Then we have the total suspended solids, which are particles larger than 2 microns found in the water column. Solids drifting or floating in the water from sediment, silt, sand to plankton and algae, organic particles from decomposing materials, and even chemical precipitates. This is a significant factor in the water clarity, and it's also measured in milligrams per liter. Then we have fecal coliforms. Fecal coliforms are measured in the most probable number in 100 milliliters, and it is one type of coliform bacteria that is found mainly in animal digestive tracts and feces. Fecal coliforms are a more specific indicator of fecal contamination of water. Then we have Escherichia coli, most commonly known as E. coli. This is measured in the most probable number in 100 milliliters, and this is a species of fecal coliform bacteria which almost always comes from animal feces. E. coli is considered to be the best indicator of fecal water contamination. If E. coli is present, then harmful bacteria or other pathogens may also be present. And finally, we have the percentage of oxygen saturation, which is the amount of oxygen dissolved in water into a certain temperature, and it is measured in percentage. This table shows some examples of the variables, and these examples show which type of variable they are. So for the first 5, we have continuous variables except for oxygen saturation, which is a discrete variable because it is a percentage. Now we're going to talk about the degree of interaction between variables. The first interaction that we have is fecal coliforms and E. coli, which are the coliform bacteria. This table shows that they are highly correlated. In this case, they both have a positive linear relationship, and it means that the two variables react in the same way, increasing. Then, for the next relationship, we have the coliforms and the biochemical oxygen demand. As we can see in these two tables, both the fecal coliforms and the E. coli have a positive linear increasing relationship, which is a very strong relationship between these variables, and we can see that they are highly correlated. And for the final relationship, we have the coliforms and the oxygen saturation. As we can see in both tables, both relationships are negative correlations, and they are very weak relations between the oxygen saturation and the coliforms.
In order to find the state with the worst water quality of Mexico, we already said that Tabasco has the lowest quality. Conagua in 2018 stated a distribution of the monitoring sites in superficial bodies of water divided by hydro-administrative regions, and there are 13 regions in Mexico: Peninsula de Baja California, Northwest, North Pacific, Balsas, South Pacific, Rio Bravo, North Central Basins, Lerma, Santiago Pacific, North Gulf, Central Gulf, Southern Border, Yucatan Peninsula, and waters of the Valley of Mexico. Conagua estimated that 70% of the bodies of waters, rivers, lakes, lagoons in Mexico are contaminated. We chose to study the southern border of Mexico because, according to a 2017 report by the National Water Commission, they stated that the most polluted river in Mexico is the Grijalva. The Tabasco territory is administratively part of the Grijalvo-Sumacinta River Basin. Tabasco is one of the states which make up the southern border region of Mexico. We are going to focus into the physical-chemical quality of the water of the rivers of Tabasco. The objective of this project is to conduct assessment of water quality trends at the local and regional levels to confirm the states with the supposed worst water quality. Conagua has a criteria for the monitoring sites that indicates the quality of the water following a superficial scale with different parameters regarding each variable separately. There are 5 different levels of the superficial scale. First we have excellent, then satisfactory, then acceptable, then contaminated, and finally strongly contaminated. These are the superficial scale for the 5 variables that we're going to study. For example, in the biochemical oxygen demand of 5 days, when we have less than or equal to 3 milligrams per liter, we have an excellent quality of water. When it's between 3 and 6, we say that the quality of water is satisfactory. When it's between 6 and 30, acceptable. When it's between 30 and 120 milligrams per liter, is contaminated. And when it's greater than 120 milligrams per liter, is strongly contaminated. For the other 4 variables, the scale behaves the same way, only with their respective values and units. As we want to see if the water quality of Tabasco is bad, we are going to focus in the last 3 superficial scale: satisfactory, contaminated, and strongly contaminated.
Now we're going to see the scientific and statistical hypothesis. For the first scientific hypothesis, we have if the superficial water has a low content of suspended solids in natural conditions and low content of organic biodegradable matter, then the water quality of its rivers is considered a good water quality. The first statistical hypothesis for this scientific hypothesis is the mean of biochemical oxygen demand during 5 days from the superficial water network of Tabasco is less than or equal to 6 milligrams per liter. We can see that the null hypothesis is mean less than equal to 6 and the alternative hypothesis mean greater than 6. Then we have, for the second statistical hypothesis, the mean of total suspended solids from the superficial network of Tabasco is less than or equal to 75 milligrams per liter. For it, we have the null hypothesis, which is mean less than equal to 75 and mean greater than 75 for the alternative hypothesis. For the next scientific hypothesis we have, if the superficial water has bacteriological contamination and residual water discharge, then the water quality of its rivers is considered a low quality. For the first statistical hypothesis, we have the mean of Escherichia coli or E. coli from the superficial water network of Tabasco is less than 850 most probable number in 100 milliliters of E. coli. The null hypothesis states that the mean is less than equal to 850 most probable number in 100 milliliters, and the alternative hypothesis states that the mean is greater than 850 most probable number in 100 milliliters. Then we have the mean of chemical oxygen demand from the superficial water of Tabasco is higher than 40 milligrams per liter, and this states the null hypothesis that the mean is less than equal to 40 milligrams per liter, and the alternative hypothesis states that the mean is greater than 40 milligrams per liter. For the final scientific hypothesis, we have the superficial water has a satisfactory quality for aquatic life and recreational use with primary contact and other uses when there are small traces of bacteriological alteration of the quality. For this, the statistical hypothesis states that the mean of fecal coliforms from the superficial water network of Tabasco is less than or equal to 1,000 most probable number in 100 milliliters. So the null hypothesis states that the mean is less than equal to 1,000 most probable number in 100 milliliters, and the alternative hypothesis states that the mean is greater than 1,000 most probable number in 100 milliliters. Now we're going to see the descriptive analysis of each variable. To the left, you can see the histogram for the variable of biochemical oxygen demand in Tabasco. You can see how the data behaves. And then we have the descriptive analysis in a table to the right. And we can see that the mean of the data is 8.928 with a mean of 2.645 milligrams per liter and a maximum of 115.8 milligrams per liter with a variance of 213.12 and a standard deviation of 14.59. Now for the descriptive analysis of chemical oxygen demand. To the left, you can see the histogram of the variable, and we can see how the data behaves. For this, the minimum is 10.71, the mean is 32.11 milligrams per liter, and the maximum is 257.35 milligrams per liter. We can see that the variance is 1,333.60, and the standard deviation is 36.51. For the descriptive analysis for suspended solids, we can see the histogram to the left and the behavior of the data. And in the table, we can see that the minimum is 10.50 milligrams per liter. The mean is 34.62 milligrams per liter. The maximum is 240.98 milligrams per liter. We have a variance of 769 0.35 and a standard deviation of 27.73. For fecal coliforms, to the left you can see the histogram and how the data behaves. To the right we can see that the minimum is 833. The mean is 8,452, most probable number in 100 milliliters. The maximum is 87,477, most probable number in 100 milliliters. The variance is 196,753,152, and the standard deviation is 14,026.87. Now, for the descriptive analysis of E. coli, we can see the histogram to the left and how the data behaves. We know that the minimum in the table is shown to be 563, most probable number in 100 milliliters. The mean is 3,819. The maximum is 17,154. And the variance is 22,767,459, and the standard deviation is 14,771.52.
To choose the distribution of each variable, we follow this methodology. This was used for all the 5 variables. First, we're gonna have the outliers detection using a box plot. Second, we verify the transformation with the probability density function plot, QQ plot, and PP plot. Third, we choose a distribution with the goodness of fit. Fourth, transform the data with the relation among the distribution table, if it's necessary, using the distribution previously chosen. And 5, choose a new distribution with goodness of fit with the transformed data. We're gonna see the biochemical oxygen demand at 5 days in Tabasco and what we did to choose the distribution. In the right side of the slide, we made a box plot for the biochemical oxygen demand at 5 days for the state of Tabasco, and we saw a big percentage of outliers. There are more than 3% of 64 of the data. We cannot remove them because we know it is not a measurement error, because it can be possible to have that amount of BOD5, which means higher than 30 milligrams per liter, the water is contaminated, and higher than 120 milligrams per liter, the water is strongly contaminated. So now we know that we cannot remove the outliers, so we have to transform. However, to confirm this and to know the best transformation for our data, we did the goodness of fit. With the empirical probability distribution plot, we can know if we have a unit distribution or a mixture distribution. This plot is telling us that the behavior shows a unit distribution. On the other hand, looking at the QQ plot, most of the data are close to the strand line. However, we have a little bit of points that do not match. Likewise, with a PP plot, we see at the center data are not close to the strand line. This indicates that transformation is needed. Using the maximum likelihood estimator, the maximum negative value of the log of the likelihood function, we found the distribution to transform. The one with the maximum value close to 0 is the best distribution. We see that the log normal is the closest to 0. Now, with the relation among the distribution table, we found what transformation we could do in our data to have another distribution. In this case, we have a log normal distribution, so we use log to transform our data. After we transform our data, we did a box plot again, and we found that there are just 3 outliers, 3% of the data. And finally, we run the goodness of fit again, and we found with a maximum likelihood estimator that log normal is a new distribution for DB05 in Tabasco. Later, we will talk about the simulations we did to confirm the distribution of this variable and the others. For DQO, or chemical oxygen demand, we made a box plot for the state of Tabasco, and we saw more than 3% of outliers, 5 in total. We cannot also remove them because we know it is not a measure error, because it can be possible to have that amount of DQO, which means higher than 40 milligrams per liter, the water is contaminated, and higher than 200 is strongly contaminated. So now we know that we cannot remove them, but we can transform. In the other hand, we have the goodness of fit, and with the empirical probability distribution, we saw that we have a unit distribution. With the QQ plot, if we look above, there are some data that is not close to the straight line, and in the PP plot, we have several points that are not close to the red line. Both plots indicate that transformation is needed. To find the proper transformation, we found the distribution using MLE. The one with the maximum value close to 0 is log normal. Then we found what transformation we could do in our data to have another distribution. In this case, we also have a log normal distribution, so we use log to transform our data. After we transformed our data, we did the box plot again, and we found that there are just 2 outliers, less than 3% of the data. Finally, we run the goodness of fit again, and we found with the maximum likelihood estimator that log normal is the new distribution for our data. Now, for the total suspended solids in Tabasco, we made a box plot, and we saw that the number of outliers are exactly 3% of 105 data. These values can be possible because having SFT higher than 75 milligrams per liter, the water is acceptable, and higher than 150 milligrams per liter, the water is contaminated. For the first time, we don't have to transform. Then we did the goodness of fit, and the empirical probability distribution plot is telling us that the behavior shows a unit distribution. On the other hand, the QQ plot, there is one value that is not close to the straight line, but this is not an indicator that our data needs transformation. Likewise, in the PP plot, we see that almost all the points are close to the straight line. This neither indicates that transformation is needed. To find the proper distribution, we use the MLE. The one with the maximum value is log normal. So with the goodness of fit again, log normal is the distribution for our data. For fecal coliforms in Tabasco, we also made a box plot, and we saw that the numbers of outliers are more than 3%. We cannot remove them because we know it is not a measurement error, because it can be possible to have that amount of CF, which means higher than 1,000, the water is contaminated, and higher than 10,000, the water is strongly contaminated. So now we have a reason to transform. The empirical probability distribution plot is telling us that the behavior shows a unit distribution. On the other hand, the QQ plot, looking above, there are points that are not close to the straight lines. And in the PP plot, we see in the center that data are not close to the straight line. This indicates that transformation is needed. To find the proper transformation, we found the distribution using MLE, and it's log normal. Now, with the relation among the distribution table, we found that the transformation is log. After we transform our data, we did the box plot again, and there are no outliers. Finally, we run the goodness of fit again, and we found with the MLE that log normal is the new distribution of our data. Now we're going to see the study for E. coli in Tabasco. We made a box plot for E. coli for Tabasco, and we saw that the number of outliers are more than 3%. We will not remove them because we know it is not a measurement error, because it can be possible to have that amount of E. coli, which means higher than 850, the water is contaminated, and higher than 1,000, the water is strongly contaminated. So now we know that we have to transform. However, to confirm this and to know the best transformation for our data, we did the goodness of fit to fit a continuous distribution. The empirical probability distribution plot is telling us that the behavior shows a unit distribution. On the other hand, looking at the upper tail of the QQ plot, there is data that is not close to the straight line. Also, in the PP plot, the behavior is similar because in the center they are not close to the red line. This indicates that the transformation is needed. To find the proper transformation, we found the distribution using MLE, and the one with the maximum value is log normal. Now, with the relation among the distribution table, we found that the transformation is log. After we transform our data, we did the box plot again, and there is not outliers. Finally, we run the goodness of fit again, and we found with the maximum likelihood estimator that log normal is a new distribution for our data. And we found with the maximum likelihood estimator that log normal is a new distribution for our data.
So after the goodness of fit, we did the simulation. We can see that all of our variables and the data follow log normal distribution, but we need to confirm this. So that's why we do a simulation for each variable, which is a sampling with replacement. With the goodness of fit test, we chose the best three distributions for the variables, which had the highest MLE. And using R, we made 1,000 samples using those three distributions in each simulation. We then ran a goodness fit test, and we saved the distribution with the highest log likelihood estimator as the final distribution. At the end of the last simulation, we obtained the frequency of each distribution. That is, the times that each distribution was obtained, and then, based on that, we chose the distribution with the highest of the frequencies. In this case, is the log normal. This table shows the simulation results for each variable. As we can see, all of them follow a log normal distribution, and this is based on the frequency of each of the sampling results. So we can see all of them are log normal.
For example, for biochemical oxygen demand at 5 days, the best three fit distribution were log normal, gamma, and logistic. And we obtained that 951 samplings were log normal, 47 gamma, and 3 logistic, and so on. When we finished the simulation, we had that all the variables follow a log normal distribution. Now that we know that all the variables follow the log normal, we can talk a little bit about the parameters. The log normal distribution is a versatile and continuous distribution. The parameters of this distribution are two: the scale parameter and the shape parameter. The scale parameter is the mean of the normally distributed natural logarithm of the data. The range is from -infinity to +infinity, and it can be found from the data with this formula. And the shape parameter is the standard deviation of the normally distributed natural logarithm. The shape parameter is always positive and is determined by the data using this formula. Despite the parameters being known as sigma and mu, they are not the mean and the standard deviation of the distribution. This distribution is a continuous probability distribution whose logarithm is normally distributed. Finally, we will say some conclusions we obtained. First, the simulation confirms that the distribution of each of the variables is log normal and also prepares us for the future analysis. Also, it is important to understand how the bodies of water in Mexico are managed and how new clean water technologies can be introduced in order to help move in the direction of the Sustainable Development Goals, SDGs, by the United Nations in order to change the world for the better. We seek to propose an efficient, cheap, and high-impact analysis to achieve quality drinking water in Tabasco. Improving water quality by removing contaminants can boost economic growth in countries and greatly contribute to poverty reduction. Some directions for future research can be the following: evaluate the performance and compliance of the regulation of pollutant control in water. Propose a water treatment designed to improve the water quality of Tabasco. Meet the water quality standards of international agreements and commitments, and evaluate the performance and compliance of the regulation of pollutant control in water. Thank you very much for your attention. This was all for today.